I left you guys thinking about inductors last time, so I should start there. So an inductor is very different from the resistor when you start doing circuit theory. Because when you have a resistor and you connect some voltage to it, the current is determined by this equation. This is what I call an algebraic equation. Just an equation in algebra, one unknown, you solve for it by dividing, and you get I at time t as V at time t divided by R. And you can make the network more complicated, put few more resistors, put few more there, few more here, resistors within resistors. Doesn't matter, because we can always, in the end, combine the ones in series, then lump them with the stuff in parallel, till the whole thing to the right of this is one single effective resistor. Then you find the current coming out of the source as V divided by that guy. Then every time it comes to a branch, we sort of know how to divide it. So resistor circuits are very easy. But now when you bring inductors, things are different. So I'm just going to tell you a little more about them. So here is an inductor. This is a symbol for an inductor. It's got some inductance L measured in henries. And the implication of that is the following. If you have a current going through this inductor, that is going to be necessarily a voltage with this polarity if the current is increasing. And the voltage you need is L di dt. This is the bottom line. Even if you skip all the other stuff about conservative forces, this is something you need to know how to do problems. The difference you notice is that the relation between voltage and current is not an algebraic equation, but a differential equation. This is called a differential equation. You don't have to worry, because I will tell you how to solve it. Because I don't know if it's a prerequisite or not for this course. But I once had a kid in summer school who, when I started using partial derivatives, got very upset and said, it's not a prerequisite. Why are you using partial derivatives? So I told him that when you come to class, there's always a danger you learn something new. You just have to learn to live with that. So I'm not going to leave you in the cold. If I do something you've not done, I will tell you how to do it. But I cannot avoid using certain notions. So this one, even though it's called a differential equation and so on, if V is a constant, we can easily find the integral. I will be V over L times T. Okay, but now we're going to be interested in cases where V is not simply a constant. It could be varying with time in an arbitrary way. So you take this guy. The first thing you notice is that the relation between current and voltage is given by derivatives. Second thing is, when a current flows through a resistor, whatever energy you provide is gone in the form of heat. It is dissipated, the light bulb glows, and that's the end. With an inductor, when you drive a current, you are building a magnetic field inside the inductor. And there's an energy associated with the magnetic field. And that stored energy will be given back to you later on. So it's like a capacitor. It takes a lot of work to charge a capacitor, because you got to take charges from this plate and keep on piling them in that plate. It's a lot of work. But then if you connect it to a bulb and you squeeze the trigger in your camera, it discharges, giving you the energy back. So the inductor and capacitor are different from the resistor in the sense in two ways. One is the voltage across the capacitor is the charge on the capacitor divided by C, which, if you like, is the integral of the current up to that time divided by C. Again, calculus comes in. So these are the two differences. The relation between current and voltage involves either differentiating or integrating, and these are energy storing circuit elements compared to this one, where energy is dissipated. So let's start with a simple problem where I have a voltage source. I'm going to take a fixed voltage V0. There is a switch, there is a resistor R, and there is this inductor L. And I'm going to assume current is flowing this way. In which case, I'm sorry, this picture is wrong. What's wrong with this picture? What is wrong? Switch is open, okay? That's what's wrong. So nothing is flowing yet. But when I close the switch, then it's fine. So, well, now it's flowing. And the question is, what does it do? How does it flow? After all, the inductor is a resistance-free wire, so you may think current equal to V naught over R will start flowing immediately, but that's wrong. That is wrong because if such a current were flowing, there'll be an energy 1/2 Li squared with that current in it, and that energy cannot come from 0 to all of that in no time. There's no way to do that. Or if you like, if the current really rose rapidly or instantaneously from 0 to some value, that's a current, di dt is infinite here. Di dt is infinite, L di dt is infinite. There's an infinite voltage needed somewhere in the circuit, and we don't have it. So that will not happen. So current will have to be continuous, start from 0, and it'll have to start climbing. The minute the current starts climbing up, it starts flowing through this guy. That is the resistance times current voltage drop across this. Therefore, the amount of voltage available to drive current through this one, or to increase the current through this one, is reduced from V naught to V naught minus Ri. That's equal to L di dt. So you can see as the current increases, the motivation to increase the current decreases because this resistor starts swallowing up more and more of this voltage. So the growth in current will be very, very slow. And we expect that after a very long time, it will settle down at some value. What is that value? We can find that value by saying, wait till the current has stopped growing. That means di dt is 0. That current will be V0 over R, and I'm going to give it the name I sub infinity because it will turn out that you will reach that value only after infinite time. But you can get very, very close to that by waiting some reasonable amount of time, and part of what we want to do is, how long should I wait? Suppose I'm settling for 90% of maximum. When does that happen? Is it after 1 second or 10 seconds or 10 hours? What's going to decide that? Well, once you have the right equations, you can figure everything out. So we're going to do that. So basically, we're going to solve the equation L di dt. So let me show you one more time how it is done, this equation. You should know how to write it. Start anywhere you like. Go around this guy. You gain voltage V naught. Then go around this guy, you drop by an amount minus Ri, you drop by an amount Ri, and here you jump from this end to this end. Remember, you never go into the inductor. That's a bad zone. That's a zone where the potential is not even defined, but I've told you multiple times that even though there are non-conservative things going on inside this, once you come outside, you just find a regular electrostatic potential difference equal to L di dt. So you drop again, then you come back to where you start. The whole thing should add up to 0, which means the equation is L di dt plus Ri equal to V0. That's what we want to solve. So when you have this thing, as I told you, solving differential equations is a matter of guesswork. There is no algorithm. You rely on what you've seen before, and you guess the answer, you put some free parameters, you fiddle with them till everything works. And in this kind of problem, we can make everything work. Some problems we cannot solve. We can write the equations, but we cannot solve them. This is something you're not used to when you take an elementary course like this one. But there are situations, for example, inside the proton there are these quarks, and the quarks interact with each other with entities called gluons. They're called gluons because they glue the quarks and form the protons and neutrons. We know the equations governing the behavior of the gluons. We cannot solve them. It's really strange. You have an equation, but you cannot solve it. It's completely possible because certain equations, every equation has a solution, but does not mean you can write it down analytically. So quite often, one may be on top of the right answer, but one may not know how to solve it, so one doesn't even know if the theory is right. So suppose this was the equation you got, but you could not solve it. It happens to be the right equation. You don't know what the answer looks like. You can never be sure this is the right equation. Similarly, when Mr. Schrödinger invented his quantum mechanics, he wrote an equation that will tell you the energy levels of hydrogen. But luckily, he was able to solve it. By solving it, he was able to show that his equation gives the energy levels in the spectra you expect from the hydrogen atom. So you have to remember that not every interesting equation can be solved. And I gave you the equation for these gluons, which we can write down but cannot solve. There is no function whose derivative we cannot take. There are lots of functions whose integrals we cannot do. That's simply asymmetry between those two. Here's a very simple function, e to the minus x squared dx from 0 to 19, or some fixed number, 0 to some x max. It has a definite value. It's area under the graph. But no one knows how to write a formula for this in terms of x max. That is a enclosed form. Okay, but anyway, this guy we can trample to death as follows. First we say, at very, very long times, the current, I told you, is V0 over R. That's when di dt is 0. So we are going to write the actual current in our problem as the current at infinity plus some difference I twiddle. Standard thing. You take out the part you know and solve for the rest of it. So let's take that assumed form and put it into the differential equation. So I get, when I do L di dt, this is a number, V over R. It has no d by dt. So di dt becomes d I twiddle dt plus R times I twiddle plus R times I infinity equals V naught. Now you can see why we did that. We did that because now these two guys cancel, and you get L di dt plus Ri equal to 0. That means di twiddle dt is minus R over L times I. So we are saying, get me a function whose time derivative looks like the function itself up to a constant. And that's something we know from high school. It's an exponential function. So I twiddle looks like some constant. I twiddle 0 e to the minus RT over L. You can take the derivative of this guy, and out will come minus R over L times the function itself. And I0 twiddle is completely arbitrary. That's not determined by this equation. That's another useful property to know. This is a linear equation. It means if you multiply both sides by 19, you get another solution, which is 19 times the old solution. So the solution's overall scale is not determined by the equation. If I give you one solution, you can multiply it by any number you like. It's also a solution, because if you multiply by a number, say 9, the 9 goes into the derivative, 9 comes here, you can see 9 times I twiddle satisfies the same equation. So we don't know this number just from the equation, but we go back to what we know, which is I of t is I infinity, which is V0 over R, plus I twiddle 0 e to the minus RT over L. But I know that at t equal to 0, this guy should vanish. T equal to 0, this guy should vanish, because there was no current when I just threw the switch. So that tells me that is equal to 0. That tells me I twiddle 0 is equal to minus V naught over R. And we get our final result, which is I of t is equal to V naught over R times 1 minus e to the minus RT over L. So at this level, you are really doing physics the way we like to do it. We like to study things, write down some equations, and solve the equations. Then we get a very precise prediction on what will happen. Because now we don't have to guess when the current will come to 90% of its maximum value. We can pick any number you like, because we can now plot this graph. And let's plot this graph, I of t versus t. At t equal to 0, e to the minus 0 is 1. You get 1 minus 1, you get nothing. At t equal to infinity, e to the minus infinity is 0. Yes?
Over on the right, where it says I twiddle subtwiddle equals
Yeah.
negative V
Yeah.
Should I do that because it's 0?
This one?
Yeah.
Yeah, right, thank you. Okay, so now this exponential, which has a full strength of 1 at time equal to 0, goes to 0 at time equal to infinity. Therefore, it takes away exponentially small stuff at very large times. And if you want to know roughly how long should I wait, the answer is the time you should wait is roughly of order L over R. Because you can write this as e to the minus r, e to the minus t over tau, where tau is L over R. Whenever you have an exponential, it'll always be e to the minus a physical quantity divided by some number that sets the scale for the physical quantity. Exponentials fall exponentially, we know that. But how long should I wait? Well, if you wait t equal to tau seconds, then it'll be 1 over e, which is roughly 1 over third of the starting value, and 1 minus that will be roughly 2/3 of its value. If you wait t equal to 3 tau, e to the minus 3 is 1 over 20, then you will be, what, 95%. So this is, you can calculate everything you need in this simple problem. So now let's come to the same problem. The switch has been closed for a long time, and the current is stabilized. So here is the switch. It has been closed. That's my V naught. That's R. And the current, you remember, is V naught over R. And this is L. So now I want to do something else. Now I want to open that switch. So what do you think will happen if you open that switch? Yep.
The inductor will resist a change in current
But how can it resist?
by inducing magnetic field
It can do what it wants, but how does it drive a current through the open circuit?
from energy stored in the magnet field.
But in what manner will the current flow, given that I've broken the circuit?
In the direction.
No, but how will it manage to go around? Because it's like removing the bridge, right? How will it go around? I agree with everything you said, but how will it make the circuit? Yes?
Be a higher concentration of charges on one side or the other.
Yeah, but how will you really get rid of the current in a circuit that seems open? Have you ever done this? Okay, that's just fine. But we know it has to get rid of that current, because otherwise, what happened to the energy? It has to go through. So you know what? You guys don't know what will happen if I pull that switch. Yes?
Does it create an electric field? Because the change in the magnetic field will create an electric field, which doesn't need the closed circuit.
Right. No, I agree it'll have an electric field. But how will the electrons flow when the wire has been interrupted is all I'm asking you. Yep?
Will the current oscillate, go back and forth?
Nope. Yes?
Would you have a static discharge?
You will have a discharge. You will have an arc. You will have a flash, and that's when you will hear a zip, and then it'll jump this gap. So whenever you remove the switch, you have to be careful that there is not stored energy somewhere. You might think, hey, I'm pulling the plug on. Well, I won't say who. You're pulling the plug, okay? And what can it do to me? Well, it can zap you, because this is a very dangerous place to pull the plug. So you know what people do? They have another resistor. Let's call this guy R1. This is R2. And R2 is a huge number, 10,000 ohms, let's say. So most of the time, R2 doesn't do anything. Because when the current comes here, in any situation, it looks at the inductor and looks at 10,000 ohms, and it says, I'm going this way. So primarily, it will all go that way. Okay? In the end, when the switch has been closed for a very long time in our old experiments, when the current is stabilized, you remember L di dt is 0 here. So there's 0 volts between these two. That's the same 0 volt across R2. No current will flow in R2. Everything will flow through L. That current, in fact, will be V0 over R, because this guy is being cut out of the loop. This is how it's going. But now if you throw this switch open, you have given it a path to discharge. So the inductor will discharge through the resistor. The current will continue to flow in this direction. Of course, it cannot flow forever because the resistor will burn up the energy. But you're giving it a path. You're avoiding, in a way, if you like, this is also a path with very, very high resistance. The air is a path with very high resistance. That means, by and large, there are no free carriers in the air. But if the two tips get really charged, just like you said, there'll be an EMF, that'll pile up charges, they're waiting to jump the gap, and eventually they'll polarize the air, which is electrically neutral, into plus and minus parts. Then the minus will go one way, the plus will go the other way. You'll recognize that as a discharge. But you don't have to worry about that now because R2 will take up your current. So now the equation we write is L di dt plus Ri is equal to 0 because if you start anywhere and you go around a loop, you have no change in anything. There's no voltage. And the answer to this one, R2. Therefore, I is equal to I0 e to the minus R2 over L times T. So now the current will decay exponentially. Again, with the time constant, R2 over L, which is the 1 over the time constant, or the time constant is L over R2. So you put L in henries and R in ohms, you'll get some time. That'll give you an idea of how many times that time you have to wait before the inductor is completely discharged. Well, it's never going to be fully discharged. It's going to take forever. But if you say, look, 1,000th of the original current is safe enough, how long do you have to wait? You put 0.001 here and see what time you get. So you want e to the minus t over tau to be 0.001. So this is how the inductor, so every big inductor you have in a circuit, you will find has got a resistor in parallel with it to take up the energy it has. So let's do a little energy calculation. Energy calculation will be, I had energy in the inductor in the beginning, which is 1/2 L I0 square. What happened to it? Well, we know what happened. There's a current in the circuit, and when the current is flowing in the circuit, it is dissipating heat in the resistor. Therefore, the power in the resistor will be I square R2. I square is I naught square e to the minus twice R2T over L times another R2. Now we integrate this power from 0 to infinity. You will get I naught square R2. The integral of e to the minus something is e to the minus that divided by that, infinity to 0. I can promise you that what you will get will be L over 2 R2. That'll give you then 1 over 2L I naught square. So this is not a surprise that the stored energy in the inductor is driving a current. So if you want one way to store energy is a capacitor, you charge it and you discharge it when you want the current to flow. Or you can have an inductor in which a current has been set up. Then when the power shuts off in your house or somebody throws a switch, that inductor can keep the light bulb burning, in fact, forever. It'll be infinite time before the bulb shuts down, but you won't be able to see anything after a while because this graph is exponentially falling. Okay, this is a very simple problem where we can do the math and we can understand what it's doing. Yep?
The graph, what is that showing here?
This one here?
Yeah.
This is called tau. You mean that symbol?
Yeah.
Yeah. Tau is a unit of time whose numerical value is R2 over L, and we can write I as I0 e to the minus t over tau. We always like to write it in this form so that if tau is equal to 100 seconds, you will have to make many multiples of 100 seconds before the current is negligible.
What are the units on the axis?
Oh, in this graph here, this is time, and this is the current in the loop. It starts out at some initial value. Okay, now I'm going to do the next slightly more complicated circuit, and that is an LC circuit. Now, if you have a circuit like that, it won't do anything. You can take these guys, hook them up, and wait all day. Nothing will happen because it's got no energy. Why should it do anything? It's just going to sit there. But if you have charged up your capacitor like that, and there's an open switch that you then closed, then the plus charges are going to leave and find their way around to the other side and neutralize them, and the capacitor will discharge. But you know that once it discharges, it's not the end of the story. So why is that? Why doesn't it stop when the capacitor is discharged? Yep.
Kind of like the inductor has momentum and it keeps pulling.
The inductor would have had a current by then. So the inductor is not going to suddenly stop having its current. So it's going to keep driving more current for a while until the capacitor is charged up the opposite way to an extent that this fights that one, that voltage, and then it'll go the other way. So it'll go back and forth. So let's write down the equation that tells you how it goes back and forth. So in other words, you should draw pictures. Now, textbooks have nice pictures, and I won't even try it. In the beginning, it may look like, in my example, in the beginning, there's an electric field here, nothing in the capacitor. After a quarter cycle, there's nothing here. There's a magnetic field in the inductor. Another quarter cycle, it's back here, but with the opposite polarity, and it goes back and forth. So we can get all that by writing the equation L di dt plus Q over C equal to 0. So let's write everything in terms of Q. Then Q dq dt is I. Because as the current flows this way, it builds up charge. That's my convention. So I can write it as L d2q over dt squared plus 1 over cq equal to 0. Now, we have seen exactly this equation before, right? We saw the equation for a mass coupled to a spring, the equation m d2x over dt squared plus kx equal to 0. There we know what it does. We know it oscillates back and forth. And L, this is an SAT question. L is to M what 1 over C is to K. It's very useful to bear in your mind this analogy, because mathematically, this equation and this equation have exactly the same solution. It's no more difficult to solve this one than that one. This may involve electric charges, that may involve masses. You don't care. So mathematically, here's an equation. Cow times d2 dog over dt squared plus, let's say, elephant times dog equal to 0, where dog is a function of time, has exactly the same solution. Because what does it matter what you call the unknown variables, right? But you got to tell me that cow and elephant are time independent, and dog is the only thing that depends on time, because otherwise the equation is not the same. So here M and K don't change, L and C don't change. So what's the answer to this one? Once again, it's a differential equation. You write dq dt squared is minus 1 over LCQ, and you're asking yourself, give me a function which, when I differentiate twice, looks like itself. There's always the exponential. There's also sines and the cosines, and you can take any combination you like, and the one acceptable solution is some constant A times cosine square root of 1 over LC t. Is that right? Yes. If you take two derivatives of q, you will pull 1 over root LC each time. Then you will get a minus sign when cosine becomes minus sign, and one more derivative will bring it back to minus cosine. So this is called the frequency, which is 1 over root LC. That's the analog of square root of k over m. Anyway, this will oscillate. It's a mechanical analog, this electrical analog of the mechanical problem. So I don't want to do too much of this because I think you should be quite familiar with this, at least the oscillatory behavior of this. And the analogy is perfect. For example, to say that I pulled the mass by 1 meter is to say that x was given a non-zero value and dx dt was 0. Analogous thing here will be q was given a non-zero value and dq dt, which is I, is 0. That means the capacitor was charged, the inductor was not carrying any current. Then I let it go. What happens? The problems are identical. Yep.
When you solve the differential equation, why did you omit the sign?
Ah.
Sign also.
Yes, so I should explain to you. That's an important point. So q of t can be one number cosine omega 0 t. Omega 0 is this guy, plus another number sine omega 0 t. And both are acceptable. And the property of this differential equation is, if I have one answer, cos omega t, and another possible answer, sine omega t, then any constant times cos plus any constant times sine is also a solution. You can verify that. If you have one solution, q1, a second solution, q2, you can add the two equations, and you can show q1 plus q2 obeys the same equation. Not only that, suppose there's one problem you solve. dq 1 over dt squared is minus omega naught squared q1. That is some function of time. And here's another function of time, obeying the same equation. Now you can multiply this by a number a, and you can multiply this by a number b. Take the a inside the derivative, b inside the derivative, and add the two sides. On the left-hand side, you will find the second derivative of aq1 plus bq2. Right-hand side, you will find omega naught squared times aq1 plus bq2. That means aq1 plus bq2 obeys this same differential equation. This is called superposing two solutions. If you've got one solution, another one, you can multiply one by a constant. It's very important it's a constant because that's what lets you take it inside the derivative. Therefore, the correct answer here is really a cosine omega t plus b sine omega t. And you can ask, why did you write a cosine omega naught t? First of all, that's not a good solution. I can put a phi there, which is arbitrary. And it's not hard to show. Let me call that c if you like, c. This can be written as c cosine omega naught t minus phi. In other words, it's possible to take either a solution with a cosine and a sine with no extra phases inside to another one with one amplitude and one phase. That phase is the delay in the cosine. Anybody here has trouble who does not know the details? I'll be happy to explain why that's correct. If you don't know, you should tell me now. You can check that if you take this thing, make a right angle triangle with A, B, and C, and an angle phi here, then A can be written as C cosine phi, and B can be written as C sine phi. And that just happens to be cosine omega t minus phi, just from some trigonometry. So the differential equation, with the second order in time, will always have two unknown parameters in it. You can choose them to be these numbers a and b, or this number c and phi. And the equation won't tell you what they are, because once you tell me there's a mass coupled to a spring, and I say, okay, this is the spring constant, this is the mass, and I ask you, where is the mass right now? I don't know, because it depends on when you started it and how you released it. So I need to know what's called initial conditions, which is the value of q or the value of x at the initial time, and the value of the velocity or the current at an initial time. With those two pieces of information, I can solve for a and b. This I think you should know. This kind of stuff you should know. So I won't say too much about that. All right. So now we do another problem. We put an alternating voltage on these guys. So this is V0 cosine omega t, and this is C, and this is L. Now we ask, what's the current? this omega is not the natural frequency of oscillation. It is some externally given omega, like 60 hertz from your power supply, from your socket. So that's driving the circuit. And you can ask, what happens now? The answer will be, you write the same equation. You can write L d2q over dt squared plus 1 over cq is equal to v0 cosine omega t. Now what are you going to do? You have to again guess the solution. So I want a function q of t so that when I take two derivatives and add it to some multiple of itself, I get something something times a cosine. So what should that function look like? Yes?
Like a driven harmonic oscillator?
No. What function q of t do you think will satisfy this equation? I'm asking for a function of time which, when I put into this, has some chance of obeying the equation. What's the functional form? Yep.
Cosine times a constant.
Right. In other words, I can take it to be some constant c times cosine omega t, period, not even times phi. Because, all right, yeah, take this one. See what happens now. When you take one derivative, you get minus omega L c cosine omega t. When you take another derivative, you get minus omega square L square. I'm sorry, this becomes sine times cosine omega t. And this one is just, oh my God, this is my nightmare. You can see the nightmare now? How many people see the nightmare? Yes? Yes. So I picked that C to be the same as this C. So we'll put a hat on this guy so we can tell them apart. So it's C twiddle over C times C twiddle is V0 cosine omega t. And what this tells you is, if you take two derivatives, I'm sorry, this is so sloppy. If you take two derivatives here, you will get plus omega square cos omega t, also with a minus sign. Q over C. Okay. You guys buy that? There is no L squared, there's just an L. That's equal to V0 cos omega t. Right? Every derivative brings an omega, and there's a net minus sign. So you find out that your guess, C twiddle cos omega t, is going to work, provided this equation is satisfied, and the cosine omega t can be cancelled. That's the whole point of doing this thing. So then you get C twiddle is equal to V naught minus V naught divided by omega square L minus 1 over C. Or if you like, minus V naught over L divided by omega square minus omega naught square. Don't worry about the numerator. Look at the denominator. The denominator says that if your driving frequency is equal to the resonant frequency, C twiddle blows up. That means when a system has got a resonant frequency, yep.
Where did the omega squared come from?
I took two derivatives. Oh, here. Oh, I'm sorry. Yes, thank you. You know, it's good to do these things slowly and not rely on what you heard somewhere. So let me do it for you again. I'm sorry about that. So this time I take two derivatives. Each one brings an omega. There's an L. And the minus sign comes because the cosine becomes minus sign. Differentiate one more, you get minus the cosine. This guy is nothing. It just says divide me by C. And that's equal to that. And then I wrote 1 over LCS omega naught square. Thank you very much. Okay? I was really hung up on the final result, which tells you you better not drive this at the resonant frequency, because then current amplitude will build up indefinitely. That's also true in a swing. If you got a swing and the kid's coming back and forth, and you're reading a newspaper, just pushing the kid, you got to push at the right time to get the best result. And that kid's not going to fly off because there's one more term in the equation for the kid, which is friction. But if you had frictionless swing and you're doing this, you got to watch out because soon there'll be nobody around because the amplitude will keep growing. Well, these are unrealistic problems, but I want you to notice one thing. Here's what I want you to notice. The voltage you were given looked like V0 cosine omega t, and the current that you got, I can obtain by taking the derivative of this charge, which is like dq dt. That's going to be c twiddle omega sine omega t. And c twiddle we can write as b naught over L divided by omega square minus omega naught square sine omega t. This is I. Here's what I want you to notice. It looks a lot like Ohm's law because the current looks like voltage divided by some number. But that's a very big difference. The voltage is a cosine, and the current is a sine. That's something I want you to think about. The current is not in step with the voltage. Whereas in a resistive circuit, the current follows the voltage. It's the same profile as the voltage, except you divide by R. Here, one is a cosine, one is a sine. That means when one guy is a maximum, other is a minimum. It's called out of phase. In fact, out of phase by 90 degrees. Yes?
When you multiply through by the C that you got, where did the omega go?
Here?
Yeah, so on the other side, so you have, when you multiply that through by the C, where did the omega go?
Oh, omega did not go. It's back. You're right. Okay, that's the omega. That came from. Okay, these problems, the only thing I'm focusing on right now, I would say of all the things I wrote there, to be the most important thing is number one, this is what I want you to bear in mind. That's why sometimes not paying attention to some constants. What is important to notice is that this is an equation you can solve by inspection. Why was it easy to solve it by inspection? Because you are trying to get in the end a cosine to balance the right-hand side. And you're trying to find a function which is itself a cosine or whose second derivative is a cosine. And we know the answer to that is a cosine. So we can guess the answer. Once you guess the answer, you put it in and you analyze the solution. You notice also that the current and the voltage are not in step. One is a cosine. You know what the cosine does. It does that. Other is a sine. So they are out of step. When one is a maximum, the other is a minimum, and so on. That means the current as a function of time is not equal to the voltage as a function of time divided by anything. There is nothing you can divide a cosine by to turn it into a sine. Whereas with resistors, you just divide by R, you get the current. Good. Now for the more realistic problem. The realistic problem has got a capacitor, an inductor, and a resistor, and no other power supply. The equation obeyed by this one will be L d2q over dt squared. That stands for L di dt plus R dq dt plus q over c equal to 0. This is analogous to m d2x over dt squared plus, I don't know how you guys wrote this in the last semester, it doesn't matter, gamma dx dt plus kx equal to 0. Notice that it's the same form. And I'm going to give this to you as a homework problem to analyze the answer to this one. So this describes a problem where you have a mass and a spring and some friction on the table. This means if you pull it and let it go, the oscillations will eventually get damped and it will die down. And the general solution for the case when it's oscillating will look like some number a e to the minus some number alpha t times cosine times some frequency omega prime t. Let me see. You can always add a phase phi, but I'm not going to do that. If you want, you can put an extra phi, but I will choose my origin of time so that I don't have that. This is what the answer is going to look like, where omega prime and alpha are going to be controlled by L, R, and C. That's the thing I don't want to do in class. Have you seen this before? Professor Harris tells me you have seen this last time. And the hints in the homework will guide you on how to do this. You just assume the solution x of t looks like some a e to the minus, I don't want to call it alpha now, beta times t. You put it into the equation and solve for beta. And you'll find beta will have a real part and an imaginary part. And you have to combine the two to get this answer. Okay, now that brings me to another thing. So I don't know how prepared you guys are for what's about to happen next, which is the use of complex numbers. So everybody familiar with complex numbers? Who doesn't know complex numbers? How do you do your taxes? So you don't know imaginary numbers? So I will tell you, I'll give you a lightning review. I'm assuming everybody has seen them in high school. I will only tell you the part you need. But I'm going to assume that I can use them fluently. Okay? I don't want to stop every time and worry about you guys. So I really need a show of hands. Anybody never seen x plus iy and x minus iy? And how about e to the I theta? You know that guy? Okay, that's all you need. So I'm going to tell you what the deal is. So everyone knows what a complex number is. We know I is square root of minus 1. Then we know that we can write a complex number as x plus iy and visualize it in the complex plane where you measure x this way and iy is measured that way. That's usually called a generic complex number z. But now, let us find the length of that. The complex number is a single point in the complex plane. The length of that is square root of x squared plus y squared. So I can also write z is x divided by square root of x squared plus y squared plus I times y divided by square root of x squared plus y squared times square root of x squared plus y squared. Just done nothing, just rearrange stuff. This is going to be called the modulus of z. And what is this? If this angle is theta here, this is really cosine theta plus I sine theta times modulus of z. And that, thanks to this great identity by Euler, is e to the I theta. Now, I don't know how much you know about this great formula that relates e to the I theta to cosine plus sine. How many people know where it comes from? What does it mean to raise e to a complex power? You know where it really comes from? Yep. Comes from power series. Turns out you can write a power series for cosine. You can write a power series for sine. Then, for example, cosine of theta is equal to 1 minus theta squared over 2 factorial, theta to the 4 over 4 factorial, over 6 factorial, etc. And you can write a power series for e to the theta, if you like, which is 1 plus theta squared over 2. This defines cosine theta in the sense that if you put theta equal to pi over 2 in this infinite series, you will get 0. And if you put theta equal to pi, you will get pi. In other words, in spite of this funny looking form, it really is the same guy. It will oscillate, it will have zeros, it will be periodic, none of it is obvious. But this power series is numerically equal to this one if you keep the infinite number of terms. Likewise, e to the theta is defined by this series. And similarly, there's a formula for sine theta. Now, once a power series is defined, you can put e raised to anything you want there. So, you know what I'm going to put there. E raised to dog It's 1 plus dog squared. This is not a joke. This is really true. This is the definition. If someone says, how do I raise e to the power dog? You do this. This will have all the properties of the exponential. It doesn't matter what's in the exponent. That's the key. People originally put real numbers. Then they put complex numbers. Now they put matrices, operators, anything you want. E raised to anything you formally define to be this infinite series, provided the infinite series converges and gives you a meaningful answer. In that sense, if you put e to the I theta here and compare the result to cosine theta plus I sine theta, it matches. That's all. I'm just going to keep using that result. Then you should also know that for every complex number, there's a complex conjugate, which is x minus iy. That means I goes to minus I. That means z, this angle theta, will change to minus theta. And given any complex number, the real part of z, which is x, is z plus z star over 2. And the imaginary part of z, which is y, is z minus z star over 2i. This is what you need to know. Every complex number has a real part and an imaginary part. In fact, z star looks like this. And if you add z plus z star, the vertical parts cancel and you get double the horizontal part. That's why you divide by 2. If you subtract and divide by 2i, you get y. Basically, that's all I want you to know, but I want you to be able to manipulate them rapidly enough. Here's something very useful about complex numbers. Let's take a complex number z1, which is mod z1 e to the I theta 1, another complex number z2, which is mod z2 e to the I theta 2. So what do they look like? Well, z1 looks like this at some angle theta 1. z2 may look like that. It's got some angle theta 2. So every complex number has a length and an angle. You can think of it two ways. It's got an x part and a y part, namely real and imaginary, or it's got a modulus and a phase. That's the Cartesian version of the number and the polar version of the number. And the connection between them comes from Euler's formula. But now look what happens when I take the product z1, z2. I get mod z1, mod z2, e to the I theta 1 plus theta 2, because exponentials add when you multiply them. Well, this allows you to immediately guess what the product is going to look like. The product is going to have a length equal to the length of z1 times length of z2. It's going to have an angle. I've not drawn a good picture here, which is the sum of the two angles, because it's theta 1 plus theta 2. So listen to this statement very carefully. When you take a complex number, say number 1, and you multiply it by a second complex number, you do two things to the first guy. You rescale it and you rotate it. So two operations are done in one shot when you use complex numbers. The mod z2 rescales the mod z1, and theta 2 adds to theta 1. Likewise, if you divide, if you take z1 over z2, it is mod z1 over mod z2 times e to the I theta 1 minus theta 2, because exponential theta 2 is downstairs. So multiplication by real numbers is very easy. You take a real number 4, you multiply it by 8, you get something in the real axis 8 times longer. You multiply by minus 8, you get something back here. With complex numbers, you take a number, you multiply another number, you rescale and you rotate. That's what I want you to know. That's going to be very important for what I'm saying. Okay, now I come to the problem I really want to solve, which is an LCR circuit driven by an alternating source, V0 cosine omega t. This is R, this is C, and this is L. And the equation we have to solve is L di dt plus Ri plus 1 over C integral I dt is equal to V0 cosine omega t. Because Q is the integral up to time t of the current. That's just Q over C. It's the same equation, but now, unlike in this problem, where I had no driving voltage, I have a driving voltage, and I've also written it in terms of current rather than in terms of charge. Because in electrical engineering, you don't really watch the charge in the capacitor, you look at the current flowing through the circuit. So you have to solve this equation. The question is, can you guess the answer? That's the only way we know. You've got to guess. You're trying to find a function, I of t, so that when you differentiate it, you get a cosine omega t. When you integrate it, you get a cosine omega t. So far, we can do it. Sine omega t will do it. But when you leave it alone, then also you get a cosine omega t. You cannot do that, because sine will become a cosine and cosine will become a sine. In the LC circuit, when you didn't have this guy, we were okay, because if you pick a sine, this became a cosine, and that also became a cosine, and you can combine them to get a cosine. But you cannot have di dt, I, and integral of I all in one equation and all satisfied by trigonometric function. The only time we can guess the answer is if it looks like V0 e to the alpha t. Suppose that was the voltage. Then can you guess the answer, what form the answer will have? It'll also be e to the alpha t times some number, because then this will look like e to the alpha t, that'll look like e to the alpha t, that'll look like e to the alpha t. E to the alpha t has a great property that whether you multiply, whether you integrate it, differentiate it, or leave it alone, it looks the same. Unfortunately, no one's interested in this voltage because it's growing exponentially fast, or if you put a minus sign, it's dying exponentially. What we really want is this. So the question is, how do we solve this problem with cos omega t? So we're going to use a certain trick. The trick I'm going to use is the following. Let me take a general case where this is some function v of t. Then, where I'm not even assuming v is real. I'm not assuming I is real, but L and R and C are real. Everything else can be complex numbers. Now, once you have an equation and you found a solution, if you take the complex conjugate of both sides, they will still match. Do you understand that? If two things are equal, their complex conjugates are equal, because this thing is the real plus imaginary. That balances the real plus imaginary on the other side. Complex conjugate just reverses the imaginary terms, so they will still match when you flip both sides. So it means if you take L di star of dt plus R times I star plus 1 over C integral I star of t prime dt prime up to t equal to V star of t. So star is the rule by which if V had a real and imaginary parts, you flip the imaginary part. So that solution for V of t implies a second equation. In other words, if the voltage V drives a current I, the conjugate of the voltage drives the conjugate of the current. That simply follows from the equation. It comes from the fact that when I conjugated it, L, R, and C are real. Do you understand that? Suppose L were imaginary or had imaginary part, then I must also put a conjugate on L. Then I star obeys a different equation, because this had L in it, this had L star in it. But if everything is real, I star obeys the same equation when you have a V star driving it. I'm almost done now. I want you to add the left-hand side to the left-hand side and the right-hand side to the right-hand side. And what do I get? Well, if I write it here, you may not be able to see it. Let me put it here then. If you add these two, you'd get L d by dt of I plus I star plus R times I plus I star plus 1 over C integral of I plus I star dt is equal to V plus V star. This again comes because the equation is a linear equation. You can always add the left-hand side and the right-hand side to get another problem where the driving voltage is V plus V star and the driving current is I plus I star, etc. But I plus I star is 2 times the real part of I. And V plus V star is 2 times the real part of V. Therefore, this implies that L d by dt of the real part of I plus R times the real part of I plus 1 over C times integral of the real part of I will be equal to the real part of V. So let me say in words what the equation means. If you, by luck, solve an equation with a complex potential V, and you get a current, then the answer to the problem where the potential is only the real part of the actual potential applied, the current will be the real part of the answer you got. That's all I want you to know. If you solve a complex problem with a driving voltage which is complex, which is just a mathematical fiction, in real life you don't have that, then the current that you get will also be complex, but its real part will be due to the real part of your voltage. And you can also show the imaginary part of the current will be due to the imaginary part of the voltage. This is just the principle of superposition. So here is the trick we are going to use. We are going to go back to original equation, L di dt plus Ri plus 1 over C integral I dt equal to V0 cos omega t. And we're going to solve a new problem. We're going to solve a problem where this is V0 e to the I omega t. And the current for that, I'm going to call some I twiddle. It's a complex current because the driving voltage is a complex voltage. So think of V e to the I omega t as the V in the previous problem. The actual problem I was given had V0 cosine omega t, but you know that V0 e to the I omega t is V0 cosine omega t plus I times V0 sine omega t. Consequently, this potential has a real part which is a cosine, an imaginary part which is a sine, and the current will have a real and imaginary parts, and the answer to our original question is the real part of the answer to this question. This is what you should think about, this part you should understand. So I've manufactured a problem with an unphysical complex voltage, and all I know is that at the end of the day, if I take the real part of the current, I'll get the answer to the real part of the potential, which happens to be the actual potential, V naught cos omega t. So why would I do all this? Why would I take a problem that's bad enough with a cosine and turn it into a complex exponential? I think you can sort of guess what the reason is. The reason is that it may be complex, but it's still an exponential. That means its derivative is going to look just the same. That means I can make a guess that the current I twiddle is proportional to e to the I omega t. So you can make the assumption that I twiddle of t is some constant I twiddle times e to the I omega t. Make that assumption and put it in this equation and see what you get. You will find you will get I omega L times I twiddle plus R times I twiddle plus 1 over I omega C times I twiddle times e to the I omega t is V0 e to the I omega t. This is because if you assume the current is an exponential, every derivative is equal to an I omega. And every integral is equal to 1 over I omega, and multiplying is just multiplying. So d by dt is got replaced by I omega, and you get this equation for I twiddle. That means you will satisfy the equation provided I twiddle times all of this is equal to V twiddle. And I'm going to write this as Z times I twiddle equal to V, where Z is the name for all the guys multiplying I twiddle. So I'll start with that here. Okay. So I wrote I omega L plus R plus 1 over I omega C I twiddle e to the I omega t is V0 e to the I omega t. Everybody get that? That's because differentiating on an exponential is just multiplying by the exponent. So this is a complex number, r plus I times omega L minus 1 over omega c. I want you to know that I in the bottom is like minus I in the top. And this is called the impedance, Z. It's a complex number. You can visualize the complex number as follows. It's got a real part, which is R, got imaginary part, which is omega L minus 1 over omega c, and the impedance Z is a complex number with some modulus and some phase. If you know the real and imaginary parts, you can construct the modulus in the phase like that. If you want this, the modulus of Z. Therefore, canceling this, I find I twiddle is equal to V naught over Z. That becomes V naught over the modulus of Z times e to the I phi, where phi is this angle defined by tan phi equal to omega L minus 1 over omega c divided by r. So don't worry too much about writing all of this down, because this you're going to find in every book. There's nothing novel or different. So this is the formula for I twiddle. Now I itself, you remember, is equal to the I twiddle of 0. I'm sorry, this I twiddle of 0. Did I define it that way? Yeah, I should write it, I'm sorry, should write it as I twiddle of 0. There's a subscript 0 there. Because the full I twiddle has got e to the I omega t in it. That looks like V0 over mod Z times e to the I omega t minus phi. But this is not the physical current, because it's the result of a complex voltage. The physical current is a real part of this without the twiddle, that we write as real part of I twiddle. Where do I get the real part? V naught and absolute value of Z are both real. Real part of e to the I something is cosine of something. And that's our answer. That's the final answer you get. This tells you that the current has a magnitude, which is V naught over the absolute value of Z, and it's got a phase phi by which it is behind the driving voltage. The magnitude of Z, for as in any complex number, if someone says what's the magnitude of Z, it is simply square root of real part square plus imaginary part square. So I want you to think about the magic of complex numbers. Your final answer has a current which is a cos omega t minus phi. Your driving voltage is a cos omega t. There is no way you can divide the voltage by anything to get that current. But in the complex language, the complex current is the complex voltage divided by the complex impedance. How does that happen? That happens because the impedance Z has got a magnitude and a phase. Therefore, if you had a voltage V naught e to the I omega t, and you divide by mod Z e to the I phi, that becomes e to the minus I phi upstairs. You're able to change the magnitude and you're able to change the phase by dividing. So if you want to take the voltage and you want to rescale it and shift its phase all in one shot, you can do it if you divide by a complex number, because a complex number will rescale this V and also shift its phase. And then you take the real part. In other words, cos omega t divided by nothing will give you cos omega t minus phi. But e to the I omega t, when divided by e to the I phi, will in fact give you e to the omega t minus I phi. So that phase shift you can produce only by dividing with a complex number. So I'll come back and explain to you a little bit more on how you do circuit problems using the complex impedance. But I think it'll be helpful for those of you who don't know complex numbers to get used to this part of it.